Hello, welcome back to EEforEveryone. Today we're going to discuss inductors. Inductors are a component that consists of a core which channels magnetic flux and some turns of wire. I like to think of inductors as a magical place where electrons go to relax after a long week. You know, take the edge off and so forth. I'd like to think of an inductor as a component that stores energy and resists changes in current. If a voltage step is applied to an inductor, the current change is zero at first, and then current builds up until the maximum energy possible to store in that inductor is achieved. At this point, the inductor conducts like a wire for DC and mostly behaves like a short circuit. When the voltage is removed from the inductor suddenly, the inductor attempts to keep the same current flowing through it. It expends the energy stored in the magnetic field to create a voltage across itself in an attempt to keep the current flowing. The larger the voltage across the inductor is, the faster energy in the inductor is depleted. Some loads can be modeled as an inductive load, and inductive loads can wreak havoc on a circuit if inductive properties of it are not properly accounted for. If current is flowing through the inductor and the current path suddenly changes to a high impedance path, the voltages that appear across the inductor can be very large, causing arcing in mechanical contacts and even destroy semiconductor devices. Solenoid coils, relay coils, and brushed DC motors are three good examples of inductive loads. If you want to create an inductor at home, it doesn't need to be anything terribly complicated. Take a ferrous nail and wrap many turns of enameled copper wire around it. This creates both an inductor and an electromagnet if DC is applied. While capacitors are very difficult to create at home with large values, inductors can be wound by hand with relative ease. I've prepared a simulation that demonstrates how inductors work and how inductors can naturally flow into the concept of a transformer. We start our journey at the beginning, the very best place to start, a voltage source stepping from 0 to 10 volts periodically. This voltage is fed into the inductor, L1. Remember, an inductor is a bunch of loops of wire wrapped around something that channels magnetic flux. Air can channel magnetic flux for an inductor, but it doesn't do this as well as other materials can. When we see 10 amps flowing through L1 and R1, we know that the inductor isn't adding any significant resistance to the circuit. Since the effective resistance of the inductor is not always the same value, we should, and will, call it impedance. The impedance of an inductor varies with changes in frequency. By plotting the current flowing through the inductor L1, we can see that there's about 20% of the on time where the current is building up to 10 amps, and a symmetrical time when no current would be flowing if the inductor was not in the circuit with the resistor. This makes sense, since an inductor can never create energy, and an ideal inductor will never consume energy. It is storing energy in a magnetic field, and then releasing it later in an attempt to resist changes in current. Awesome! When we introduce a switch into the scenario, things do get a little more complicated. Now instead of a changing voltage, we are using a model of a switch to connect and disconnect the inductor L2 to V2. When the switch is closed, current should build through the inductor just like before, but when the switch opens, there's no opportunity for current to flow. Since there is an open circuit, the inductor will be unable to maintain a constant current no matter how high the voltage across it becomes. At first glance, the current through L2 looks like one might expect. The switch is closed, current builds. The switch opens, and current stops. However, there is one critical detail that is being overlooked. Let's plot the voltage at the node connected to the top of the inductor L2. Oof. 10 kilovolts could cause us a lot of problems. In an attempt to maintain a constant current, the inductor produced a large voltage. If the switch were the contacts of a relay, this high voltage could cause arcing, significantly shortening the life of the relay. If this relay were a semiconductor device, it could be destroyed the first time it ever attempted to turn off the current through the inductor. So this is bad. We can't switch the inductor off without damaging semiconductor or mechanical switches. How are we going to work with inductive loads? Surely there must be some way to safely dissipate the energy stored in the inductor. There is. By adding a freewheeling diode, D1, across the inductor such that it does not conduct when the inductor is switched on, it will allow the energy stored in the inductor to safely dissipate by allowing the inductor to draw current through the diode when the switch turns off. Plotting the current through the inductor L3 shows a very similar image to what we saw in the first example, but we need to look at the voltage across the diode to see if we've eliminated the potentially damaging high voltage condition caused by the inductor in the previous example. Sure enough, the negative voltage has been reduced to the forward voltage of the diode. This makes it possible for a mechanical contact or semiconductor device to safely turn off the relay without fear of multiple kilovolts of potential being applied across it. This, naturally, leads us to transformers. In the previous examples, we were very careful to make sure that the inductors didn't get too close. It always goes the same way. First, they have no idea where the other inductor is. Then they're just friends for a while. One thing leads to another, things get intertwined. I think I had a snack. And a few months later, a transformer. Now we don't need to concern ourselves with how transformers are made. It's a difficult and awkward conversation for anyone to have. Ask your mother. When two inductors are placed such that the magnetic flux from one inductor also flows through another inductor, a transformer is created. A transformer is sometimes more accurately described as coupled inductors. A transformer does not have a direct connection from one winding, or inductor, to the other. There is only the magnetic flux and parasitic capacitance linking the primary and secondary windings of a transformer, assuming that something hasn't gone horribly wrong. Let's use ideal inductors and an ideal core for our discussion, which operates under the assumption that 100% of the magnetic flux from one inductor passes through the other inductor as well. Let's go back to our switched inductor example, but this time we'll add a perfectly coupled inductor with a resistor as well. This looks like a nonsensical circuit, since there's no voltage or current source connected to L5. Let's assume, just for a moment, that I haven't completely lost my marbles yet, and probe the voltages and currents here to see if there's more going on than meets the eye. The current through L4 looks a lot like the previous switched inductor. If this inductor was behaving the same as before, we would expect to see a few kilovolts across the switch when it turns off. But now it's only 10 volts? That's odd. If there's only negative 10 volts, then where has all the energy stored in the inductor gone? Let's take a look at the current through L5. Whoa, it appears like the energy stored in the inductor L4 was suddenly transferred to L5 when L4 was no longer allowed to conduct current. Plotting both the inductor current L4 and L5 makes it clear to see that the same total sum of current flowing in this configuration is the same as what was flowing after the freewheeling diode was added to the switched inductor. This is pretty neat. I mean, it's not very useful, but it's neat. I wonder if there's a more practical way that we can use the energy stored in the inductor. By adding a diode D2 and capacitor C1, we will attempt to store the energy we're passing from L6 to L7 when the switch opens. This burst of current should cause charge to build on the plates of C1, and therefore the voltage across C1 should increase. The diode will prevent the energy stored in C1 from being removed when the switch turns on again. We can see bursts of current passing through D2 and L7, causing the voltage across C1 to climb, cycle after cycle. If we had a way to monitor this voltage and adjust how much energy was put into the inductor L6, we could attempt to create a constant voltage across C1 regardless of the load current being taken from it. This is the basic theory of operation behind a flyback converter. A flyback converter is a very specific flavor of switch mode power supply. When making a switch mode power supply, the switching frequency is much higher than what we're using here, and this allows the inductor and capacitor to be much smaller. That said, the same principles still apply. In fact, almost every topology of switch mode power supply depends on the ability of an inductor to store energy and then release that energy later by producing a voltage which attempts to keep current flowing in the same direction. Now, if you think that inductors are cool and this video is great, let me know by hitting the like button on this video, subscribing to the channel, and leaving a comment letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. Bye!